A very good morning to all of you. I am Bipin Kumar Mishra from the Department of Mechanical Engineering, IIT Kanpur. I am here to present our paper, the titled Characterization of a Propeller Slipstream at Low Reynolds Number. Propeller slipstream is found in many applications, including turboprops, UAVs, drones, and since the UAVs are deployed nowadays to solve the common people problem in many sectors like communication, agricultural sector. So it is necessary to optimize them for better performance. And in that aspect, the propeller slipstream study is more important. I am here showing the effect of propeller slipstream on the turboprop wing. And when there is helicoidal wake is falling over the wing, they change the nature of the nature of the boundary layer locally. And because of that local change, it creates the global change of drag and lift by changing the local angle of attack. Now, evolution of these blade wakes is highly dependent on majorly three parameters. Advance ratio, that is the ratio of forward speed of the aircraft to the rotational speed of the propeller, number of blades of the propeller, and pitch and blade shape. And from maritime propeller study, we can see here the advance ratio variation and also the variation in the wake. Here at the bottom, you can see the number of blade change. If the change in number of blades, the how wake look, it is different for all blades. And here you can see when pitch variation is there, there is variation in the distance between two helicoidal blade wake. Higher the pitch, larger the distance. But since maritime propellers, due to shape, size, its study is not relevant to the UAV drone propeller slipstream study. So to characterize the UAV drone propeller slipstream study is much more important in case of UAV drone applications. And in that aspect, one study is reported by Dieter Seltan. They have used two kind of advance ratio ranges for zero advance ratio and non-zero. Zero advance ratio means when there is no incoming free stream speed, but propeller is rotating like in static condition. In static condition, the results obtained from this advance ratio, they have concluded that the advance ratio, the slip stream is expanding up to more than a radial distance farther from the plane of rotation. And also for using the different blade geometry, it doesn't affect the much axial velocity profile behind the or downstream to the propeller. But in advancing condition, they have found that slipstream does not expand more than 40% radius distance from the plane of rotation. And the blade, that axial velocity profile is highly dependent on blade geometry, as well as when advanced ratio increment is there is lower thrust generation. But this study did not report lower advance ratio, since advance ratio increment leads to higher thrust and the different way. And also, they didn't measure the slipstream very near to the plane of rotation. And also, there is no report of turbulence profile as well as wake width growth downstream to the plane of rotation. To tackle all this, I am here presenting my paper where I have measured the slipstream at very near to the plane of rotation, like 8% of radial location to 1.18 times R, and 8 fixed advance ratio of 0.45. Here is my original setup, and its schematic is reported here. These are the measurement locations in the radial, and these are the streamwise. Here I have used the single axis hot wire to measure the slipstream. And for that, for axial velocity measurement, I have used this configuration, and for tangential velocity, this configuration is used. Now coming to the data acquisition, I have used sampled the data at 25 kilohertz and sampling time was 40 seconds. And hardware low pass filter was used 10.4 kilohertz, as well as the uncertainty is also calculated, and that is found at lowest calibration velocity is 1.75%. Now, during the acquisition of the data in the slipstream using hardware, I have also monitored the RPM and with IR, infrared sensor, this obstacle sensor, and its output is shown in here. When there is no object, there is 0 volt, and when there is when there is object, there is 0 volt, and otherwise there is 5.3 volt. And the RPM versus number of rotation, you can see the RPM is much closer to what I have said. Now coming to the axial velocity time trace, here U represents the instantaneous velocity and non-dimensionalized with free stream speed. And in that result, you can see that slipstream is quite periodic at all radial location, except this is motor wake, where the highly turbulent nature of the wake is found. And slipstream is like there is two part, one is unsteady laminar part and one is turbulent wake part. Unsteady laminar region, the velocity is having temporal deceleration and acceleration in the near mid-wake region for the same for the very near to the plane of rotation. But when you approach towards the tip for the same plane, you don't see any much change, like no acceleration or deceleration in the laminar portion of the wake. For the tangential velocity time trace, here V is also shows the tangential velocity, instantaneous tangential velocity, non-dimensionalized with free stream speed again. Here you can see there is not much acceleration or deceleration in the laminar part. Even you are here very close to the means mid radius region at the same plane, but there is increment in the swirl is there. But here motor wake is different, like it is much more periodic than earlier one. And when we approach towards the tip, there is not much acceleration and deceleration again found, but also there is lack of swirl velocity. Now coming to the mean velocity profile, U is mean velocity at particular location and non-dimensionalized with the free stream speed. And for all streamwise locations, it is plotted, and you can see from the plot that the slipstream is contracting and the maxima is occurring around the mid radius region. And slipstream is contracting, but at the same time, outside the slipstream velocity is decreasing to maintain the continuity. In the right hand side, there is a swirl velocity profile, and you can see that during the slipstream contraction, swirl is increasing to conserve the angular momentum, but very farther distance, like after the 0.98 hour, there is not much like after 0.5 or 0.6, sorry, 0.5 or 0.6 hour or 60% of the radius location from the plane of rotation, you don't see much change in the swirl. That is lack of swirl, and that lack of swirl is also observed by Dieter Settle for the advance ratio of 0.6. And in this profile, the mean velocity profile, they have also observed the contraction, but after the 50% of the radial location, because they haven't measured the very near to the plane of rotation, as I have already discussed. And in this swirl velocity profile, the maxima occurring at very closer to the root here, around 30% of the radius location. Now coming to the turbulence profile, you have already seen that mean kinetic energy is increasing, but here turbulence kinetic energy is decreasing, and turbulent intensity is very exclusively, very much exclusively focused on tip vertex. And tip vertex is when you approach farther distance from the slipstream plane of rotation. When you approach farther distance from the plane of rotation, then you see that the tip vertex is convecting towards the axis. And in the right hand side plot, the turbulent kinetic energy is also decreasing same way, but the tip vertex signature is only very much prominent after the 98% of the radial location from the radial location streamwise. Now coming to the segregation of turbulent and non-turbulent part, the velocity signal acquired at this location like 29% of the radius, it is shown here. In that, from the velocity signal, I have segregated the turbulent part and non-turbulent part from this signal to calculate the blade wake width. So from here, this red portion you see, this is the blade wake portion and this is unsteady laminar region. From the blade wake portion, I have taken the mean velocity of this portion and as well as the time for it appears. So multiplied both, I get UWTW, and time averaging over 40 seconds, I get the mean wake width. And that mean wake width is plotted here in the y-axis, non-dimensionalized with the chord length of the propeller, chord length of the blade at that particular location of interest. And for 7 streamwise location, it is plotted. And from this plot, you can see that the wake width growth is non-monotonous in streamwise direction. As well as second thing is that the tip vertex wake is growing much faster than other locations. So from this study, we concluded here that the slipstream is periodic in nature. It is contracting as well as the swirl is increasing up to certain distance to conserve the angular momentum. And here the contraction is happening to, and also we observe that the velocity is lower outside the slipstream to maintain the continuity. And in the wake width plot, we saw that key wake width growth is non-monotonous in nature, as well as the wake width, that vertex tip wake growth is much more prominent than other locations. And also the turbulent kinetic energy is decreasing since mean kinetic energy is increasing, but turbulent kinetic energy is decreasing. So that's how I have concluded here. And thank you very much for listening.